We will start in a few minutes. I hope I'm audible. We will start the class in 2 minutes if nobody else will join. This is the week 9th of our classes. In our last class, we discussed about quantum mechanics, and this time we will be discussing about reciprocal lattices. This concept will be very important from the next class onwards. We will be discussing about how the waves interact with periodic uh, potential wells. There's something called the chronic bending model, which we will be discussing. We will explain the observation of band gaps in semiconductors. We'll start in a minute. Hello, Karthik.
Hello, sir.
Hello. We'll start in a minute.
Okay, sir.
Okay, let's start. So, this is the week 9th. We will be discussing about reciprocal lattices in this class. So the first question is, though moving from the Drude model to the Drude-Sommerfeld model, the electronic contribution to the specific heat capacity at constant volume was corrected, but still directionality of which of these options was ignored. The exterior of the solids, basically the dimension of the solid, the wave vector, incoming and reflecting radiation, the crystal structure.
B.
Yes, the answer is crystal structure. So so both the Drude model and the Drude Sommerfeld model are free electron models. We have discussed it several times in the past. So the Drude model is for classical particles, where we use the Maxwell Boltzmann statistics. In the case of Drude-Sommerfeld model, we use the concept of
Fermi type.
fermions, which are quantum particles, and we have the Fermi-Dirac statistics. Now, quantum particles, we know from the de Broglie hypothesis that these particles have dual nature. They are particles and waves. And so then what we did is we said if electron is a wave, and so if we have a confinement, we can find out the energy levels. And for that we solve the Schrodinger equation to find out the energy levels. Now in all of this, the actual for the actual crystal, we'll have several of this ionic cores, right? There'll be like potential like this. There's a ion. These are ion locations. Till now, we have ignored the interaction between the nearly free electrons and the and periodic and periodically arranged ionic core. And this will become very important because we will see later that this is the why, like we will have something called the chronic penny model and all, which we'll be discussing in the subsequent classes. And we see that this is very important to study the effect of this nilly electrons, the wave nature with the periodically arranged ionic cores. And we had a question in the last class also that this is what determines the crystal structure. So this is something that we have not yet discussed, which has to be discussed, and we will be doing it in the upcoming classes. So the answer is we have still not studied about the interaction of the electronic, so the wave nature of the electrons with the periodic ionic potentials, which is basically the crystal structure. The answer is option D. The next question is, the finer aspects of interaction between waves and crystal structure are explained better by using reciprocal space than real space. It's more like a qualitative question. We'll be moving into quantitative questions later.
Yes, yes, true.
The answer is true. So this uh, waves have something called the wave vector. So as the name suggests, it's a vector quantity, and if you take the absolute value of this, if it is a wave vector, if we take the absolute value of this wave vector, It's 2 pi by lambda or 1 by lambda, depends on the convention. Let's just say, okay, let's say it's like 2 pi by lambda. Then we see that the dimension of this wave vector, which is basically is inverse of length. So it is the is in the reciprocal length unit. And so if we have uh, a system, a coordinate system with reciprocal length as an unit, it will be very easy to study the waves. Therefore, waves are easy to study in reciprocal space. Whereas the real crystal structures are in the real space, because we know in terms of like length, if we have an associated lattice parameter which is in angstroms, which we if it's in the real space, it's in the real space. So in order to study them both together, we need to bring them to the same coordinate system. We can either study, we can either choose real space, or we have to choose the reciprocal space. And we have to convert both of them to the same space to study their interactions. However, we find that you would also see in the lectures that when we study the reciprocal space, we get some good explanations for the diffraction theories. And so, in the reciprocal space, we can this the final aspect basically like sort of an example of final aspect is the diffraction, which is understood in a much better way when we study in the reciprocal space, in the reciprocal space rather than the real space. So answer is true. The next question is, reciprocal lattice vectors are dash of the spacing between the corresponding planes. So it's reciprocal to the spacing, it's negative of the spacing, it's equal to the spacing, or it's opposite of the spacing.
Reciprocal.
Yes, so as the name suggests, it should be reciprocal. So let us discuss about it. I'm sure it's in the notebook also, but let's discuss about it. So let us say we have a coordinate system uh, with three unit vectors a1, a2, and a3. So this so let them be the let a1, a2, a3 be real space that is vectors. So from the definition, so this is a definition that has been given. In reciprocal space, so we can write it as let it be b3 and similarly we can write for other vectors also. So from this, if we take this individual terms, now we have this, we can uh, redraw this. So we have this a vector, it's the a2 vector, and we can make a parallelogram. And when we do this a1 cross a2, this is basically the area of this parallelogram, and it has a direction that is perpendicular to the plane of a1 and a2. This is the direction of, and so if we now look at in the first term for the reciprocal lattice vector b3, from this equation, from this figure, we see that, let this be a2, this be a1. So b3 is in this direction somewhere, a3, and so we take the dot product in this direction. So what we get, this is dot product, and so this becomes the direction of b3. So what happens is that, and then it's a dot product, and it's in the denominator. So this term is basically, it's a formula for calculating volume in the vector space. It's the volume of unit cell. It's in the real space, and this term is the area of the base. So this, if we write it, and we see that it's in the, and we take the dot product of a3 along this vector. So basically b3 is the base area where the base area into perpendicular distance, sorry, so spacing between adjacent planes. And we know that the shortest distance between two planes is the perpendicular that we can draw between them, which is basically the height of, or the planar spacing between these two planes. And so b3, if you take the modulus, and also there's a direction, because it's, so I didn't write it in the modulus form, so the unit vector perpendicular to basal plane. And now, so if we take the modulus, it simply becomes 1 by the spacing between adjacent planes. So spacing between the, so they call it corresponding planes. It's the same thing as adjacent planes. So basically, the spacing between corresponding parallel planes. So the answer is A. The reciprocal lattice vectors are reciprocal of the spacing between the corresponding planes. Even this is in real space. This is a reciprocal space. Now we are talking about the magnitude of a reciprocal lattice vector. So in this case, the reciprocal lattice vector is defined by this, denoted by this capital H value, which is a vector. So it's a vector in the reciprocal space, and what is its magnitude? 1 by DHKL, 1 by so first one is just the scalar value. B and D are the vectorial values. Is it the 1 by DHKL or DHKL? Which of this is the correct answer?
B, sir. Mm, B.
Okay, so one thing. So we're talking only about the magnitude, right?
Magnitude. Then A.
So it won't be a vector term basically.
Okay.
So yes, so answer will be either this one or this one. And if it was okay, and the answer is basically A. So we have already like sort of solved it in the previous question in a not so rigorous manner. So anyway, let's solve it. Let's solve it again. So first of all, we have to define what is what is the DHKL. Let's go step by step. So what is DHKL? What is this vector? So we have these two terms. So let's study them one by one. So let us start with the reciprocal lattice vector H bar HKL. So if we have a start with DHKL only. So let's say we have again in the real space three vectors. Let them be the unit vectors a1, a2, a3. So they are a1, a2, a3. So these are unit vectors. And if we have a plane, HKL, basically H, K, and L are Miller indices. So the way that we define them is that if we have a plane here, let's say, and this is the origin, and this is, let's call it A, B, and C. So this is the plane. Then the points at which it intersects. So this OA, OB, and OC. So OA is A1 by H, OB is A2 by K, and OC is A3 by L. So this is the definition of a plane uh, designated as this HKL. So, hmm, let's put up here. Hmm. So uh, now if we look at this image, we can draw. Let me see if I can copy it. Copy, paste. Okay. So we can have another plane which passes through the origin. And the way that we define DHKL, the way that we define DHKL is basically the perpendicular distance between these two planes. This is DHKL. So this is how we define the term DHKL as the distance between two parallel planes. Now coming to the H bar HKL. So it is a reciprocal lattice vector. According to the question, so we can write it as H into the reciprocal lattice vectors B1, K B2 plus L B3. Now since all of these are lattice vectors, so H, K and L are integers. So now we have to find the direction of this HKL. So if you would have gone to the class, the way that it is done is if you do, let's say, OA plus AB vector, give this OB vector. So if you want to find AB vector, it is OB vector minus OA vector. So OB vector is A2 by K minus A1 vector by H. So this is this is one of the edges, the AB vector. So now if you do a dot product of HKL, this is the value of HKL. So HKL dot AB vector. We see that we have K here, so we know that A1 vector cross B1 vector is equal to 1, and A1 cross B2 is 0, and all this. So for the same, so A1 cross A1 dot B1 is 1, A2 dot B2 is 1, A3 dot B3 is 0. So using this rule, we find that for all HKL similar to this HKL dot BC and HKL dot AC equal to 0. If you put in the values, because A2, so if you look at this thing, so A2 dot B2 is 1, and K into K, this they multiply and it becomes they cancel each other. So we have 1 minus 1 because there is a negative term here. So 1 minus 1 becomes 0. So what this means? This means that the HKL vector is perpendicular to all the three uh, lines, and therefore what it means is that the HKL must be perpendicular to this. And also we have said that DHKL is the perpendicular spacing between them. So HKL will also be in this direction. This is the direction of HKL. And from the image, we can directly say that DHKL lies on HKL, but anyway, we'll solve for it. So what we do next, we then say, okay, so what we found? We found that HKL is perpendicular to plane HKL. And to find out the magnitude, so if n star is the unit vector along HKL, we can write it as the magnitude of the vector divided by the magnitude of the vector. So now to find out the distance, we can say that if we take the component of OA in along H, so if we take the component of OA along the direction of HKL lattice, then we'll get we'll get the value of the magnitude of this vector. So if we do that, magnitude of the lattice spacing. So this is basically A1 by H. This is basically A1 by H is OA, and then along this direction, perpendicular to the planes. A1 by H dot the unit vector along the reciprocal lattice vector. So this is A1 by H dot product HB1 plus KB2 plus LB3 vectors and by the magnitude HK. So again A1 dot B1 will be 1 and H will cancel. So we see that DHKL is equal to 1 by magnitude of HKL. So the answer is option A. Magnitude is inverse the lattice spacing. And we can also see from here, I hope this image is clear, that DHKL is the distance between two planes, in which one of the planes lies in the origin and the other plane ABC is the adjacent plane to that, the adjacent parallel plane to that. The vector, the reciprocal lattice vector is perpendicular to all the three lines AB, BC, and AC, which lies on the plane HKL. And so we say that the HKL is perpendicular to the plane ABC, or plane HKL. And since DHKL is perpendicular spacing between them, it also lies along the on the same vector, and we can find it by taking the component of OA along the reciprocal lattice vector. It's already in the book. I hope it's clear. Karthik?
Yes, sir.
Okay. The interaction between the wave vector and crystal structure conveys information about which of these physical observations: reflection, diffraction, absorption, and transmission.
Diffraction.
Diffraction. Yes, so I just wanted to discuss like what is the difference between reflection and diffraction. So reflection, it is sort of a surface phenomena, because in both of them sort of similar thing happens. Like you have an incident light, and then there is a light that comes out, or it may not be light, like any kind of a wave. There's an incident wave, and then there is a wave that comes out of the sample. So it can be either reflected or it can be diffracted. In the case of reflected, it's a surface phenomenon, and it happens seen at all angles. Diffraction is a bulk phenomenon, which is why the crystal structure becomes important. And it is seen at only some specific angles. What are those angles? So you can find out those angles using the Bragg's law in real space, or then you have this Lawes criterion. Lawes condition in reciprocals. It's basically where we draw the evolved sphere and find out if the if the difference of the incoming and the outgoing vectors is a reciprocal lattice vector or not. So yes, so the interaction between the wave vector and the crystal structure gives information about diffraction. Oh, so okay. So I already mentioned it in the previous question. So Bragg's law is used to understand which of this behavior in which space. Understand reflection in real space, diffraction in reciprocal space, diffraction in real space, a reflection in reciprocal space.
Diffraction in real space.
Yes, so it is about, we talk about diffraction in real space. So anyway, let's discuss about it. So what it says is that if there is a if there's a plane of atoms and so on, like the bottom also, and then we have a wave incident wave, and then there is a diffracted wave, and this is the angle theta. And then even in the bulk also, this waves will come and waves will go, and so there's a path difference here. So if this is the distance d and this is theta, then this becomes theta. So this is d sine theta, and even this is d sine theta. So if the net path difference 2d sine theta is a integral multiple of the wavelength, then we will see constructive interference. If it's an integer, then we'll see constructive interference, which results in diffraction. So diffraction. So this is all in real space because we see that the distance is d, which is like a length unit, and it's not a reciprocal length unit. So this is well understood. So uh, let's. I just wanted to say that you can sort of reach the same conclusion in the reciprocal space also. So let's say we have this equation, and you can. So we can rewrite it as 2. So if n is equal to 1, 2d sine theta is equal to lambda, or we can write 1 by d is equal to 2 into 1 by lambda into sine theta, right? So if you go to the lowest condition in reciprocal lattice, okay, maybe I should write down the lowest condition here. I didn't write it here. So the lowest condition says that diffraction occurs when condition for constructive interference. Okay. The change in wave vector is a vector of the reciprocal lattice. It's a statement form of the evolved sphere concept. So what it means is that if there is a diffracting wave vector, and if you subtract it with the incoming wave vector, then this should result in a wave vector that is a lattice, that is a reciprocal lattice wave vector. That was, so if this, so the change is a reciprocal lattice vector. This is the lowest condition. Now if we, now let us draw this equation in the next question. So again we will draw the spots, but this time in the reciprocal space. So let us draw the 2 spots here. It's in reciprocal space, so the distance is 1 by d. That is where the LHS come from. Here 1 by d. So we have a incoming. Let us come to this later. Okay. So we have the incoming wave vector. We have the diffracting wave vector. And so if you want to draw k diffractive minus k incoming, you can take the opposite of this and then sum it up, which is basically this thing. This is minus of k incoming, and this becomes the k vector that we have discussed in the previous question. This is the lattice. So this is the condition for diffraction, and this is 1 by d. And as we had discussed earlier, this is theta, and this k, both of these equal to 1 by lambda. To find out the magnitude of the k vector, the capital K vector, which is this one, equal to, so both of them are equal because there is no loss of energy, both lambda are same. So this is equal to 1 by lambda sine theta, and for this and this it's 2 times, which is same as the Bragg's law. You can see here, these two equations are same. So this is in the reciprocal space, and we reach the same conclusion, which is given by the Bragg's law. Bragg's law is in the real space, and the von Laur's condition is in the reciprocal space. Did you understand, Karthik?
Yes, sir.
Okay. A diffraction condition based on Evol's sphere construction will be satisfied by which lattice points? Always one lattice point, all lattice points, sphere contacting the lattice points, or the maximum lattice points. So these are reciprocal lattice points. So how?
Sphere contacting.
Yes, it's a sphere contacting. So this is what it looks like. So we have the incoming. This is the incoming. This is the diffracted, and so we can draw again kf minus ki. So basically we can draw like this. This is minus ki. So kf minus ki will be this q vector in this image, which should be a reciprocal lattice vector. Now this, depending on in which direction if you can move the crystal, or you can change the incoming wave's direction. So this 2 theta. So the leaving wave vector can be on any of these points of the circle or sphere in 3 dimensions, and only when it intersects a certain point, we get diffraction. So for example, we get diffraction when it's in this one, when it's in this one, and it, okay, it slightly misses, but maybe this one, because there's a certain broadening associated with it. If it was an infinite crystal, then we wouldn't have seen any diffraction from this, but for finite sized small crystals, we'll see that diffraction from this. So there's one thing. So this spot sizes. So if the spot size was this big, then we would get a much more like even if the wavelength changes. So from the wavelength that is corresponding to this radius to this radius. So we have a much more. We will see diffraction from many more points if the sizes of these points was larger. So what determines the sizes of this point? So it comes basically from the Fourier's expansion, Fourier series. So for smaller crystals, we have a large spot sizes. So these are larger size for small crystals, and vice versa. So for an infinite sized single crystal, this will be a single point. So for smaller crystals, you will get many more uh, diffraction spots. Is it clear what I mean to say in this? By the sizes of these spots?
Yeah. Yes, sir.
Okay. So if let's say if it was if the in this case the crystal, as you can see, is like a cube sort of a thing, and so it has a like a spot. Now if it was a disk with a very thin disk, then what will happen? Let's say it is X, Y, and Z. The reciprocal lattice will actually, in the reciprocal lattice point will actually be extended like this. It will be extended in the Z direction, and it's a point object in the X and Y direction. So basically the shapes of these points and the sizes of these points can also vary. Maybe I'll keep it here. So we have another question on evolved sphere. So the evolved sphere in three-dimensional reciprocal space indicates the all possible diffraction conditions.
True.
True. We discussed here, like wherever the evolved sphere will intersect a point, we will see a diffraction happening in those conditions. So this is S0, where lambda is basically incoming wave, incident beam, and this is the outgoing beam. So you must have seen this equation in your lectures. So what all terms do this like? What do they signify? These two vectors. So which are properties of the wave they consider? Is the question clear? Okay. So basically, I'll just write it down here. This is the diffracted beam or the leaving beam. So S0 by lambda is the arriving beam, and S by lambda, which is a vector, it's a leaving or the diffracting beam. And when this is diffracting only when So when this is a reciprocal lattice vector. Only then we have this, we can call it a diffracting beam. Or this is just a leaving beam. Uh, Understood, right? I mean, there was not much in this question.
Yes, sir. Initially, I didn't get, but
Huh. So this is actually taken from the notes. That's why it's in S, not an S format. So to end, we have a, I think it's an easy question. So how many lattice points per unit cell are there for this FCC simple cubic and body-centered cubic structures in real space? Like how many lattice points are there in a simple cubic, in a body-centered cubic and a face-centered cubic? So for simple cubic, basically simple cubic is this sort of a structure, and we have a unit cell at all the corners. Sorry, points at all the corners. So the number of unit cells is, and each of these points is shared by 8 other cubes. So the number of lattice points in simple cubic is 1 by 8 into 8. So 1. There's only one lattice point for the simple cubic structure in real space. For BCC, there's also 1 in the center. So we have 1 by 8 into 8 plus 1 is the body center. These are the corners. This is 2. So body-centered cubic structure has 2 lattice points per unit cell. In the case of FCC, we have again 8 in 8 corners, and we have 6 faces, and they are shaded by 2 unit cells. 2 unit cells. So we have half into 6. So these are the 6 faces of cube. Basically 1 plus 3 equal to 4. So a real structure FCC will have 4 lattice point per unit cell. So the answer is A,
A2C3.
A2 C3. The answer is B. So one interesting thing is that if you now convert these structures to reciprocal space, I'm not sure if it has been done in your classroom. Reciprocal space, then FCC becomes BCC structure, simple cubic remains simple cubic, and BCC changes to FCC structure. Has this been done in a class, this derivation?
Yeah, yes, sir.
So this is one interesting thing that you will find out when you will try to solve for the reciprocal lattice vectors. Okay, I think this was the last question,
Yes, sir.
and we're also at 4 o'clock. So I think we can stop here.
Okay, sir.
Any questions or anything?